let's start with that wheel, the wheel that we have over there for just a minute. Oh, I'm doing a terrible job. We'll say this white thing is the wheel. That'll work for now. And its center is here. And there's the piece of blue tape and the piece of green tape. Now, when it's spinning, and we said it was, rotating one rotation every 2 seconds, right? That's what we were saying about that wheel. One rotation every 2 seconds. I was giving you its speed in rotations per second. Now, I don't know if you guys know this, but you understand that RPS would be rotations per second, and the P in that means that the per part goes on the bottom. So when I say per second, we're saying to put the seconds on the bottom. Does that make sense? And that would suggest that RPM would be rotations on the top and minutes on the bottom. Does that make sense too? So these are two rotational speeds, rotations per second and rotations per minute. So I gave you the speed of the wheel in rotations per second because I said it made one rotation every 2 seconds, which means its actual rotations per second is 0.5 RPS. Everybody got that so far? Well, at any one instant when we were watching it, these two things had a speed that was tangent to their path. Tangent to their path. I don't know that you know that phrasing. So consider the blue piece of tape. The blue piece of tape was going around a circle that looks like that. Does that make sense? At the instant that I've frozen it here, that blue piece of tape was going in that direction that I've indicated with the arrow, right? This is what's its direction, right? For that instant, that was its velocity. But an instant or two later, it was over here going this way with a new velocity, right? The direction of its velocity kept changing, but its velocity was always tangent to the circle it was traveling on. So I haven't been saying it like this, but we are actually comparing a rotational motion with a tangential velocity. That's the word I should be using. I haven't been because it's a complicated sounding word and I want to add complication to it. But tangential simply means that it's moving in a straight line, but there's a curve there, so it has to keep changing its direction. Imagine this. Imagine you were running on a path. Okay, so this is a path. We're looking down on the path, and you're running on this path. The instant that I see you here, you're probably running that way. But you're not going to keep running that way because you'll run off the path, right? So a few instants later, you might be here and you're now running this way. But you're not going to keep running that way because if you do, you're going to run off the path, correct? Of course, here, you'll be running this way. And you can probably keep running that way for a while because the path looks to be straight there, right? But when you make it here, you're running this way, but you're probably going to have to change direction because you're going to run off the path. So a few seconds later, you're running this way. Whenever you have a velocity and you freeze your velocity for that instant, your velocity is always tangent to the path you're on. This is always true for all velocities. You're always tangent to the path you're on. When the path is straight, the tangent lines up with the direction of the path. But if your path is curved, you can't stay running at that direction because you need to change direction to follow the path. But your velocity is always tangent to your path. So in the ones down here at the bottom, you don't want to run off the path, so there has to be an acceleration this way to change your direction. accelerations are always going to have to be towards the center of curvature if your path is changing. If your path is straight, you don't need an acceleration because you don't need to change direction. But when your path is curved, there has to be an acceleration in the direction of the path. So the acceleration we're talking about here is that centripetal acceleration that we talked about a couple days ago, but we call this velocity the tangential velocity because it's always tangent to your path. So that's what we're finding over here when we're talking about finding the velocity. We're talking about finding the tangential velocity, the velocity you have for that one instant before your direction changes. Is that okay? All right. Now, the way we do this is by unit multipliers, which has nothing to do directly with physics. It's something you probably learned in chemistry. We're going to use unit multipliers. But unit multipliers require knowing a conversion fact. Now, I didn't say it like this when I first introduced it, and I probably should have. Our conversion fact for this is going to be 2 pi r meters or centimeters or inches. That's all decided by what r is measured in. Is going to be equal to 1 rotation. That's our conversion fact. Now, the reason I wrote meters, centimeters, and inches, I want to be really careful. What if I gave you a radius that was in centimeters, but I asked you for the velocity to be in meters per second? You will still have to do other conversions. You follow me? But to do this conversion, remember, this is the conversion fact. There are lots of conversion facts. For example, you know this one. 1 minute is how many seconds? So, see, we know lots of conversion facts. How many centimeters until I have a meter? Or how many meters until I have a centimeter? Do you guys know? King Henry died by drinking chocolate milk. I have no idea what. Oh, that's the mnemonic for. Okay, excellent. Is that really helping? All right. The way I learned it was different. So I don't know. It won't translate because it was a long time ago. I don't remember most of it. I just know that centa, centa is 100. Like when you celebrate a centennial, you're celebrating 100 years. So there are 100 centimeters in 1 meter. It's sad that I have to explain that, but it's okay. I had to explain it in 6th period too, so it's okay. I will get over it. You know lots of other conversion facts, but the conversion fact itself is something you can look up. Does that make you right? I'm not too worried about that. Believe it or not, the conversion fact is also on your equation sheet. So when you get your equation sheets on your next test, the conversion facts are on the first page. Now, if I want to convert from 0.5 rotations per second to meters per second, I would have to know something about the way the thing is rotating. I would have to know where it is on the rotating object. Right? That's going to be necessary because that's here in the conversion fact. We need the radius. Everybody okay with that? All right. Let's do an example. Has anybody ever seen one of these records before that has the big hole in the middle? Do you know what they're called? Well, all records would be considered vinyls because they were made out of plastic. So even the long plays and the small ones would be considered a vinyl. But these had a different name to them. And I don't know if they, like I said, I don't know if you guys know or not. What's that? No, not CDs. That's a compact disc. It's different completely. These were a vinyl. They had a big hole in them, and they had the little grooves on them like a long play, but they had a big hole in the center, and they were singles or 45s. That's what they were called. They existed when I was a kid, and they've never really brought these back, but they've brought back the long play records, the big ones. Now, the reason these had a big hole in the middle And if you go to like an old record store, you'll see lots of these. This is what they would send to radio stations for DJs to hear the song. So if an album came out and they released a single, meaning they released a song off of the album to be played on the radio, they would send that to the record to the radio stations for them to play it, and that's how it would be played. They would also send it to distributors who had jukeboxes. Jukeboxes used to play records, and the mechanism used to play the records required a big hole in the center so that the mechanism could lift the record up, turn it over, and then play it. If you had a little hole in the middle, it would break the it would eventually break the record. So the big hole allowed for a bigger spindle that could do this over and over and over again. So that it would go to a different record, pull that one out, play it. Now, the 45s were called 45s because they spun at 45 RPM. That's why they were called 45s. You had to switch your record player from 33 1/3 to 45 to play a 45 RPM. Now, they were small, the radius of about like 3 inches, so they're about 6 centimeters to the edge. So here's a question. I would like to know how fast the edge of a 45 is moving when the disc is being played. That's the question. I'll say it again. I want to know how fast the edge of a 45 is moving when the disc is being played. We're going to convert from the rotational speed of the disc to the linear speed of the edge. All right, this is our example. So again, the question I'm asking that I'm hoping you guys will figure out, and I'm going to work it with you, is how fast is a point on the edge of the record going? What is its tangential velocity when the record is being played? Everybody have the problem in their head? So the first thing I want to do is I want to write out what I know about the speed. I know the current speed of the disc is 45 rotations per minute. I'm going to write it like a fraction on purpose because I want to split up the stuff that's on top of the fraction with the stuff that's on the bottom of the fraction. Now the other thing I'm going to do is I'm going to kind of write out my destination. I want to end with meters and seconds. I want to know how fast the point is moving in meters per second. I'm writing my destination out there to help guide me on this trip because I want to convert this from rotations per minute to meters per second. Everybody see what I'm trying to do? I'm going to use unit multipliers. Now, if you haven't done this before or you didn't do it this way in chemistry, that's okay. A unit multiplier is just another fraction. Each fraction is going to do one conversion at a time. Now, sometimes you might have to do multiple conversions, but we're going to treat each conversion as a separate multiplier. So you'll notice I just put a blank fraction up there, and I'm going to convert one thing at a time because I noticed I'm going to have to convert minutes to seconds and rotations into meters. So which thing do you want to convert first? So I heard everybody say all sorts of stuff. So we'll do rotations first. Is that okay with you guys? So I'll remind you of our rotation fact from earlier. Our rotation fact is 2 pi r is going to be in the units of whatever your radius is. So this one's going to be centimeters is equal to 1 rotation. So remember, this unit is whatever your radius is given in. That may not be what your answer has to be in, but that's whatever your radius is given in. So that's going to be our conversion fact. So to use the conversion fact, we want to get rid of rotations. So whatever you're trying to get rid of, you have to put it on the opposite side of the fraction. So I want to get rid of rotations. And rotations is on the top part of the fraction. So in my multiplier, I put rotations in the bottom part of my fraction. Got it? And then whatever I'm going to be left with, I put on the top. I'm going to be left with centimeters. Put that on the top. Now I put in my conversion fact. 1 rotation is 2 pi r. Can I put the 6 in there and that's going to be okay? 2 pi r centimeters. So that's my conversion fact. Now here's the thing. When I put that in there, in my head, I'm tracking the fact that the rotations are going to be canceling out. So when I'm done, right now, I'm at my first stage of my conversion, and my answer would be in centimeters per minute, because that's what's left, right? Centimeters are on top and minutes are on the bottom. That's not what I want for my destination, so I got to keep going. So what's another conversion you want to do? Okay. So we can do the centimeters next. Is that okay? All right, so I make a new fraction. I notice that the centimeters are given to me on the top, so I want to get rid of them. I'll put centimeters on the bottom. And I have a conversion fact that will go to meters. So this will be the destination, right? We're going to be done when we get there for the meter part. But now I have to put my conversion fact in here. And from before, we know that for every 1 meter, there's 100 centimeters. Okay? That means the centimeters are going to cancel out here. Getting closer. Now we're in meters per minute. So only one thing left to convert, right? So we're going to convert the last thing. I'm going to need another one of these. And I notice that minutes are on the bottom. So to cancel them out, I need to put minutes on the top. And I want to be left with seconds. Oops. Seconds. Then I put in my conversion fact. For every 1 minute, there are 60 seconds. All right. Now you multiply all the things across on the top, and then you multiply all the things across on the bottom, and then you divide. Now here's the thing, and I mean this with all my heart. You guys are great, and you'll do this, and then we're all going to get different answers because you screw it up the moment you start getting into your calculator. So type it into your calculator, then turn your calculator over. And I'm going to write the answer up here. Then you turn your calculator back so you'll have the evidence in front of you of what you screwed up. Got it? All right. We're going to convert from the rotational speed of the Earth to a point on the edge of the Earth. You down for this? Now you're going to have to know what the rotational speed of the Earth is. Do you know what it is? Oh, yes you do. Don't say no. I bet it makes one rotation every 24 hours. You really said no? Well, the way I said what? The rotational speed of the Earth, it's one rotation every 24 hours. And I want to know in meters per second how fast the Earth is going. All right, so do you want me to help you with this, or do you think you guys just do it? All right. Go, try it. You might have multiple conversions. I'm going to help you, because you didn't know what the rotational speed of the Earth was. I'm going to put something on here that you may not know. Did you know that 1 hour is 60 minutes? Okay, just checking. I wasn't sure. All right, try. Now, I know you guys are working, but like I said, I would really like to get to another point. So, one of those, and maybe one of those, and how about one of these? Did you do all those things? Now, if you do all those things and you calculate her right, you should get that. If you calculate her wrong, that's got to be on you. That can do it too. That's why I said this one's going to be tough, but we're going to be doing planet stuff as a second part of our unit. So we'll be doing big numbers. It's good to practice. All right, 5 minutes. This one's important to me. And I'm going to cut this example down a little bit because I want to get to the gist of it. So you guys have been to Busch Gardens? They have the carousel, and there's horsies on it. They have a 3-horsey carousel with like 3 horsies on it. The one at like Magic Kingdom's a 4-horsey carousel, so it's a little bit bigger. At Busch Gardens, this is 2 meters. This one is 3 meters, and this one is 4 meters. Okay? Now we don't have time to do as much of this as I wanted, so you're gonna pick your favorite one, because I don't know which one you would ride. You might be scared and want to be on the inside. You might be fearless and be on the outside, and you might be a moron and ride the camel, which doesn't go because it doesn't go up and down. It's lame. Who rides the camel? I believe it. No, she rides the bench. What's that? they're not for everybody. I find them, I mean, I've been on a lot of carousels because I had little kids, and little kids go on carousels. So, and I always tell you to put the little kids on the inside carousel. We're going to see why. So here's what I want you to do first. Pick one of these. Anyone you want. If you're a dad like I was for a long time, I still am. You'd stand out here with your camera and you'd wait for them to come around so you could take their idiot pictures as they come around. And they're all having fun because they're little kids. And in Busch Gardens, it takes 4 seconds for it to go around. So it makes one rotation every 4 seconds. Okay? Pick your favorite horse. Tell me what the tangential velocity of the horse is. Okay? Whatever one you want. Pick your favorite. Tell me what the tangential velocity of your horse is. The zebra. All right, did you get your favorite? Did you pick one? So did you get 3.14 if you're on the inside horse, or 4.71 if you're in the middle horse, or 6.28 if you're on the outside horse? Excellent. Now, I've got 1 minute. You guys have to see this, please. The whole crux, the whole reason we did this. If you're on one of these horsies and we're looking at you, you have weight, you have normal force, but you also must have a force towards the center because you have to hold on to the horse. How much force is required for you to hold on to your favorite horse? Right, the whole point of doing this was so that we could have the tangential velocity to figure out force. So if you'll notice, we know how to do the tangential velocity part now. I want to know if you can figure out what the holding force is. That's the one towards the center. It's not much more to do now. You see what you have to do? Let's assume that you guys are a svelte 50 kilograms. Just a little over 100 pounds. Some of you probably a little more. Some of us a lot more. I'm proud of all the food I eat. But some of you may be a little less, and that's okay. Give it a shot. Let's just all use 50. Pick your horse, use 50, see if you can get the right answer for how much force there is.
Yeah, Ava, pick your bench. Ava, fight back, bro.
Okay. That's the bell, but did you do it? Did you put your velocity in there squared, put the radius in there, then multiply by the mass to get it? If you did, the inside one is 246, the middle one was 369, and the outer one is 493. Check your work. We'll practice some more next week.